Yeah. Well, math in general, right?
Yeah.
But discrete math is a good one, because it's one that focuses on proofs. All right. So earlier in the chapter, at the beginning of this chapter, quick review for you. Well, actually, even before the chapter. So one of the ways that we've been used to proving or disproving a statement, proving a statement is false, is with a counterexample. Right? You remember doing counterexamples? And I say something like, every integer is even. Is that true or false?
False.
False. How do you know?
1.
1. 1 is an integer, 1 is not even. Therefore, the statement is false. You just found what we called a counterexample to the statement. Right? In this section, we're going to be focusing on a smallest counterexample. A smallest counterexample. So what is the smallest counterexample to every integer is even?
1.
Negative.
What about negative 1? That's less than 1. What about negative 3?
I guess.
What about negative 10 trillion and 1? What's the smallest counterexample to this statement? There isn't one. There isn't a smallest number that proves a statement wrong.
Small.
So it's right.
You mean like smallest number of value?
Yes. As in, if I put, what do I mean by A is smaller than B? I mean A is less than B. That's what I mean by smaller.
So smallest counterexample, is that like?
You know what this statement is false with the counterexample. 1 is a counterexample.
Okay.
Negative 10 trillion and 1 is a counterexample. What's the smallest counterexample to this statement? There isn't one.
Negative infinity.
How do you know it's even?
1, that's not an integer. 2, how do you know it's even or odd?
Because with every even comes another odd.
So there'll be an odd after the infinity, if it is even.
Okay. This does not have a smallest counterexample. So today we're going to be focusing on, we're going to be doing proofs with counterexample proofs. We're going to be doing smallest counterexample proofs. And smallest counterexample proofs are not something you can use everywhere, always, forever. Now, if I were to change this from integer to natural, every natural, meaning natural number, is even.
Zero.
Is this statement true?
No.
No. What's the smallest counterexample?
1.
1. Now 1 is the smallest counterexample. So when we're using a smallest counterexample proof, one of the things you're going to notice is we're often talking about the natural numbers. Okay? And that hopefully gave you intuition for why so far. Alright. Another thing we're going to be doing in these smallest counterexample proofs, we're going to be doing proofs by contradiction. So let's remind us of what a proof by contradiction is. How do you do a proof by contradiction? You remember proof by contradiction?
Yeah. You just make sure that it implies a false statement.
Rather than showing alpha implies beta, you show alpha and not beta is impossible. If it is impossible for you to have alpha and not beta, then if you have alpha, you must have beta. If having alpha and not beta leads to an impossible worldview. So it's impossible for you to have alpha and not beta. If that's impossible, then if you have alpha, you must have beta. The intuition clicking for what these two statements are saying?
Yeah.
Fantastic. Okay, so with that, we're ready to introduce the well-ordering principle really quick, and then move on to our intuition for these counterexample proofs. Now, what is the well-ordering principle? Hopefully pretty intuitive to you. We already kind of used it up here, but now let's make it explicit. The well-ordering principle states that every non-empty subset of natural numbers has a least element. Every non-empty subset of natural numbers has a least element.
Okay.
Take all the take all the odd natural numbers. That is a subset of the naturals, right? Is there at least one element in there?
Yeah.
Yes. So there's a least element in there, namely 1. Take all the even natural numbers. Is that a subset of the natural numbers? Yeah. Is there at least one element in there? Then there's a least element in there, namely 0. Take all the natural numbers less than negative 10.
Okay.
Is that a subset of natural numbers?
No.
Yes. Does it have an element in there? No. It's the empty set. So it does not have a least element.
Say that again.
Take all the natural numbers less than negative 10.
Okay.
Should we draw them out for you? Here they are.
Oh.
There's all the natural numbers less than negative 10. It's a subset of the natural numbers. Is it a non-empty subset? No. It's empty. So does it have a least element? No. So every non-empty subset, if we put a natural in there, every non-empty subset of natural numbers has a least element. Now this is not something we prove. If we were developing a system of mathematics, this would have been an axiom. Or if you were developing something like calculus, you'd have a logically equivalent axiom that gave you this. But something to this effect has to be given as an axiom. It's not something that we can prove. But it appeals to our intuition very nicely. This is not true for the integers.
Yeah.
Let's look at all the even integers. That's a subset of the integers. What is the least even integer? There isn't one. Because for any small integer, small even integer you choose, I can always find a smaller one. You can't find a smaller even natural number than 0. Good?
Okay.
Okay, so that's a well-ordering principle. And so it's using the well-ordering principle up here that we were able to find a smallest counterexample. Intuitively speaking. Okay, so now this section we're going to be doing proofs over and over again using a smallest counterexample, a small statement that makes the smallest natural number that makes a statement false. And here's roughly what those proofs are going to look like. This is just an outline of the proof. This isn't an actual proof. Over and over again, what's going to happen? We're going to want to prove that every natural number has some property P. Some statement about natural numbers, P. How are we going to prove that that is the case? We're going to let A be the set of all natural numbers that don't have that property. With me so far? I'm trying to prove that every natural number has a property P. How am I going to start my proofs? I'm going to let A be the set of all natural numbers that don't have that property. If every natural number has a property, then A will always be an empty set. You with me? So A here will always be an empty set if every natural number has a property P. Anyone getting lost by a set notation here? Let's just state it out explicitly so you understand. Let A equal the set of all natural numbers such that it is not the case that property P applies to N. Okay. What do we do over and over again? We assume, by way of contradiction, that A is not empty. We know A is empty. We assume by way of contradiction that A is not empty. Not missing anyone. Then, since A is a subset of the natural numbers, how do I know that A is a subset of the natural numbers?
Because it says the ends in the natural numbers.
Yeah, by definition, let A be a set of all natural numbers such that. So, A is a subset of the natural numbers by definition, and A is not equal to the empty set. We assume that by way of contradiction. So if A is a subset of natural numbers and it's not empty, then, by the well-ordering principle, A has a least element, we call it X. You with me? Those pieces of logic are probably what's going to be hard about these proofs, is going through that right there. Then once you have your element X, we show that X being in A implies some false statement, some contradiction. Therefore, A must be empty. Therefore, if A is empty, then P must apply to every natural number. A is a set of all natural numbers that that property didn't apply to. A is empty, therefore it applies to every natural number. That's big picture how the logic goes. So these pieces I have right here are pretty boilerplate for each of these proofs. And then how you go from your X to proving a contradiction is where the thinking comes in. So let's see a concrete example of this. And hopefully that helps. All right, we're going to prove that every natural number is even or odd. So there's our property. Our property is even or odd. We're trying to show that applies to every natural number. Right? what do? We start by let A be the set of all natural numbers that don't have that property. Let A be the set of all natural numbers. Let A be the set of all natural numbers n such that n is not even or odd. It's not even and it's not odd. It's not even or odd. You with me?
Okay.
How many natural numbers are not even or odd?
0.
0. So we know in our heads A is an empty set. There are no natural numbers that aren't even or odd.
Yep.
Right? We assume by way of contradiction that A is the empty set. Or that A is not the empty set. We know A is the empty set. We assume by way of contradiction that it's not the empty set. And we're going to show that leads to an impossible worldview. Therefore, A has to be the empty set. We're showing it not being the empty set is impossible. So, assume by way of contradiction that A is not the empty set. Now, since A is a subset of naturals, how do I know that?
Definition.
By definition, A is equal to all the natural numbers such that da. But we can only choose from the naturals. So everything in A has to be a natural number. So since A is a subset of natural numbers, and A is not the empty set, then, by the well-ordering principle, A must contain a least element, we'll call it X. You with me? Okay, what do we know about X?
Is the least number of A.
It's the least element of A, and A is a set of all the natural numbers that are not even or odd. So what do we know about X?
Does not even or odd.
It is not even or odd. And we're going to get a contradiction out of that. Okay, so X is the smallest thing in A, and we know that X is not even or odd. Observe that 1 is odd, right? So whatever X is, it has to be greater than 1. Sorry, we're starting in the wrong place. I should have done 0 there. Observe that 0 is even. So whatever X is, it has to be greater than 0. X is the first, if we were to start listing out the natural numbers, X is the first natural number we'd come across that's not even or odd. 0 is even, so whatever X is, it has to be greater than 0. You with me? Okay. So, since X is greater than 0, then X minus 1, if I know X is greater than 0, then X minus 1 is what?
0.
It's greater than or equal to 0. No, X right here could be 100, so then X minus 1 would be 99. But the smallest possible value X could be is 1, and so the smallest possible thing X minus 1 could be is 0.
Okay.
In other words, we know that X minus 1 is a natural number. And we know that X minus 1 is not in A. How do I know that X minus 1 is not in A?
Because it is even or odd.
Well, we don't know that yet. How do I know that X minus 1 is not in A? What was X?
The least element of A.
X is the smallest thing in A. Is X minus 1 smaller than X?
Oh, yes.
Yeah.
So then X minus 1 can't be in A. If X is the smallest, if I say that Hayden is the smallest student in my class, you know Debbie can't be in my class. Right? If X is the smallest element in set A, X minus 1 cannot be in set A.
Yeah.
Okay.
Okay, so since X minus 1 is not in A, then X minus 1 must be even or odd. A was a set of all the natural numbers that aren't even or odd. X minus 1 is not in A, therefore it must be even or odd. You follow that logic there? Alright. So then, X minus 1 is even or odd. If X minus 1 is even, what does it mean for X minus 1 to be even? It means that there exists some integer A such that X minus 1 equals 2A, right? Now I'm going to solve for X by adding 1 to both sides. So X is equal to 2A plus 1, which means X is odd.
Yeah.
Up here, we said X is in set A, which means it's not even or odd. Here we said X is odd. Contradiction. Let's look at the other side. If X minus 1 is odd, what does that mean? That means that there exists some integer A such that X minus 1 is equal to 2A plus 1. Now we're just going to solve for x by adding 2 to both sides.
1 to both sides.
Or adding 1 to both sides, thank you. Factor the 2 out, which gives me that x is equal to 2 times an integer, which gives me x is even. So if x minus 1 is odd, x is even, and if x minus 1 is even, x is odd. Either way, x is even or x is odd. But we said up here, x is not even or odd. X is even or odd. So then, x is not even or odd, and x is even or odd. There's our contradiction. There's our false. That's impossible. So we made a bad assumption. What was our bad assumption? All the way at the top where we said A is not the empty set. So therefore, A is the empty set. What does that mean? That means every natural number is even or odd. Because if we look at the set of all the natural numbers that aren't even or odd, we get an empty set. Right?
Yeah.
If I say everyone with green skin come stand at the front of the class and no one stands at the front of the class, that means no one had green skin.
Right.
A is a set of all the natural numbers that don't have that property. If the set of all of them that don't have the property is empty, then they must all have the property. That's logic. So we just proved that every natural number is even or odd. Make sense? All right. Let's move the camera and do all these other proofs. Not sure how many of these I'm going to crank through. All right. Yeah, go ahead. All right. Next one. We're going to prove that every integer now is even or odd. And we're going to use this proof to prove this proof. So this is not a proof by smallest counterexample. This is just for completeness sake. So now, how are we going to prove that every integer is even or odd? This is going to be a direct proof. Let x be some integer, and observe that x is either greater than or equal to 0, or x is less than 0. Grab a random integer x. My job is to show that this integer x is even or odd.
Okay.
Notice I can divide the integers into those greater than or equal to 0 or less than 0, right? Now, if x is greater than or equal to 0, if I pick an integer that's greater than or equal to 0, that's the same thing as picking a natural number. So if x is an integer greater than or equal to 0, x is a natural number. And we just really proved over here that every natural number is even or odd. So x is even or odd.
Yeah.
Good? Now we need to handle the negative case, where x is less than 0. If x is less than 0, then negative x is greater than 0. Let's make sure we understand the logic of that. Give me an integer less than 0. Negative 5 is less than 0. That means that negative 5 is greater than 0.
Yeah.
So if x were negative 5 in this case, x being less than 0 is the same as this. If x was negative 5, then negative x is greater than 0.
Yeah.
So, up here, if x is less than 0, then negative x is greater than 0. And so if negative x is an integer greater than 0, what do we know about negative x? It's a natural number. Yes, negative x is a natural number.
Oh, yeah.
Because x is a negative number. Negative x is a natural number. Don't be confused just because we put a negative sign in front of something. That doesn't magically mean it's less than 0. All right. So, negative x is a natural number, which means that negative x is even or odd, but that's not what we were after. We need to show that x is even or odd, not negative x is even or odd. So I know negative x is even or odd. I need to use that fact to show x is even or odd. If negative x is even, what does that mean? That means that there exists some integer a such that negative x is equal to 2a, and I'm just going to solve for x. So multiply both sides by negative 1. Factor out the 2. And now I have x is equal to 2 times some integer. Therefore, x is even. So I just barely showed if negative x is even, x is even. No surprise there. You're already comfortable with that. Let's move on to the next one. If negative x is odd, what does that mean? That means that there exists some integer a such that negative x is equal to 2a plus 1. Now I'm just going to solve for x. So negative x is equal to 2a plus 1. Multiply both sides by negative 1. Gets me there.
Okay.
Good. Now I'm going to rewrite negative 1 as negative 2 plus 1.
Okay.
So that's going from there to there. We just replace negative 1 with negative 2 plus 1. Now, from these two integers, I'm going to factor out the 2. So x is equal to 2 negative a minus 1. So notice that that's negative 2a minus 2 plus 1.
Yeah.
You follow that? I just factored the 2 out of these two numbers. So when I distribute back in that 2, 2 times negative a gets me my negative 2a. 2 times negative 1 gets me back my negative 2. And my plus 1 and my plus 1 are still there. So what do I have? I have x, down here. X is equal to 2 times some integer plus 1. That's the definition of odd. Therefore, x is odd. And we're done. Therefore, every integer is even or odd. Follow that? Alright, let's do some more smallest counterexample proofs now. We have these 4 to do. We'll just crank through them, I guess. Hopefully we remember this summation notation. Let's make sure we remember this. If I were to write the sum from k equals 1 to 6 of k squared, what's that equal to?
1 squared plus 2 squared.
What's he doing? So he says first we plug in the 1, which gives us 1 squared. And then we're summing, so we're going to add what we get when we plug in the next integer. So we plugged in 1, now we plug in 2 for k. Now we plug in 3 for k. Plug in 4 for k. Plug in 5 for k. Plug in 6 for k. And then stop when we reach our top number. Remember that notation? Now, common trick that you're going to see me do over and over again, so let me get you comfortable with it. If I were to write the sum from k equals 1 to 5 now, of k squared. So this right here is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, right?
Yep.
And if I were to add to that whole thing, if I were to add 6 squared to it, then that would now be the sum from k equals 1 to 6 of k squared. You see that? Mm-hmm. This is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, and then we have plus 6 squared. It's the same thing as 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. Follow that? Alright, we're going to be doing manipulations like that in these proofs. So, just want to introduce you to it. Introduce you to this notation. Because we're done writing these things out as big, massive sums by hand. Okay, so let's do our first proof. We're going to prove, and remember, these proofs by smallest counterexample are going to be proofs about the natural numbers, over and over again. So we're going to prove that for every natural number, the sum from 1 to n of 2k minus 1 is equal to n squared, where n is greater than 1. So first let's read the statement and understand what the statement is saying. This is saying the sum of the first n odd integers is equal to n squared. In other words, if I add up the first 3 odds, I'll get 3 squared. What are the first 3 odds?
1, 3, 5.
If I have 1 plus 3 plus 5, then I'm going to get 3 squared.
Cool.
If I add the first 3 odds, I get 3 squared. If I were to add up the first 5 odds, I would get 5 squared. Right? 1 plus 3 is 4, plus 5 is 9, 9 and 9 is 18, plus 7 is 25. Right? Okay, that's what we're proving in general. Let's make sure that you see that that's what we're proving in general. We'll write out one of these sums explicitly to help you see it. So imagine I had the sum from k equals 1, and we'll just pick a number for n this time. This time we'll pick 4. So sum from k equals 1 to 4 of 2k minus 1. What does that equal?
1 minus 3 plus 5.
Plug in 1 for k, and we get 1 plus, now plug in 2 for k. 2 times 2 is?
4,
Minus 1 leaves us with
3,
3. Now plug in 3 for k. 3 times 2 is?
6,
Minus 1 is? Plus, plug in 4 for k. 7, right? 4 times 2 is 8, minus 1 is 7, and we're done. So this was adding up to 7. If I replace this with an n, then we continue with this plus dot 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 plus till we get to our very last term, which would be 2n minus 1. Where n's any natural number. Right? That's what this sum's saying. So now let's write out what we're proving. Hopefully we're comfortable with the notation. What I'm doing a proof that for all n in n, comma, the sum from k equals 1 to n of 2k minus 1 is equal to n squared, and actually this is only true for n greater than 1. In other words, it doesn't hold at 0. Why does it hold at 0? Let's try plugging 0 in really quick.
Can you go down with the k?
No. So this ends up in empty. I guess we could do it at 0 then. We'll just leave it at 1. It still works at 1. Alright, so 1. We're doing proof by smallest counterexample. How do I start every proof by smallest counterexample?
by some way of contradiction that there exists without the property.
First, we're going to define our set A. We're going to follow this exact pattern over and over again. So 1. Let A be the set of what?
All numbers and natural numbers.
It's going to be a set of all natural numbers such that what?
Put in that summation thing.
Where is that sum? Such that this statement is false. Probably would have been easier to just write the statement.
Yeah.
Maybe you don't understand what it means for that statement to be false, so I should write out for that sake. Just think of that as well. But that k equals 1 is getting in my way. K equals 1. Such that the sum from k equals 1 to n of 2k minus 1 is not equal to n squared.
Yeah.
And we also want n greater than 1. We're getting more 0. So maybe we wrote out a few cases, right? We went all the way up to 5. Maybe if we went up to 26,000, it suddenly doesn't work anymore. Maybe it just happens to work for the first 26,000 numbers and then stops. Right?
Yeah.
That's possible. It might just be weird that for the first 26,000 numbers, when you add them up, if I add the first 26,000 odds, I get 26,000 squared. Maybe that's a weird coincidence and it suddenly stops being true. Kind of like all prime numbers are odd. Are all prime numbers odd? No. 2. 2 is a prime number and it's even. It's the only even prime number. Maybe there's secretly some natural number out there that then makes the statement false. You with me? So we're going to prove that that is not the case. So let A be the set of all natural numbers that make the statement false. 2. Our second line. Assume, by way of contradiction, what?
That A is an empty set.
That A is not equal to the empty set. Well, if A is not equal to the empty set, what do we know?
There's something
A's
in
and
there.
the natural numbers.
We know A is a subset of the natural numbers. We know it from the definition of A. It's only made up of natural numbers. It's all the natural numbers that happen to make that statement false. So we know it's a subset of natural numbers and we know that it's not empty. What does that mean?
There is a
That's the
smallest
even or
number.
odd.
Yeah, smallest element.
Oh, that's not what we're proving.
Yeah, we're doing what we do over here, over and over again. A is a subset of the natural numbers. And there's something in A. Therefore, it has a least element. So then A has a least element, and we'll call it X. Alright, now what?
We show that X and A is false.
Yeah, we need to show that this is impossible. Something being in A is impossible. Well, we already tested this on 1, right? Observe that the sum from k equals 1 to 1 of 2k minus 1 is equal to what? Just 1. The sum of the first one natural, or the sum of the first one odds is 1, is equal to 1 squared. So it satisfies, 1 satisfies this equation.
Okay.
When I plug in 1 here, I got 1. When I plug in 1 here, I got 1. That's what I have right now right here. You see that?
Yeah.
So observe that 1 satisfies the equation, which tells me what?
But it said the n has to be greater than 1.
Oh, sorry, greater than or equal to 1. I meant greater than 0. Thank you. Greater than or equal to 0. Can't believe I made that mistake. Good catch. We were just ignoring 0 here. So that's why I started with 1. So observe that 1 makes the statement true. Now, A is a set of all the natural numbers that don't make the statement true. 1 makes the statement true. So
The X is less than 1.
So 1 is not in A.
You okay?
You with me? So that gives me that 1 is not in A.
What's stopping it from being 0 again?
The definition.
We just chose by definition to just only deal with natural numbers greater than 0. Okay? Alright. So then if 1 is not in A, then what does that mean? That means that X must be greater than 1.
Okay.
Right? Because 1 is the smallest positive integer. And if 1's not in A, and A is just a set of positive integers, then the smallest thing in A has to be greater than 1. You follow logic there? So X is greater than 1. Kind of wrote that weird. X is greater than 1, which gives me that X minus 1 is greater than or equal to 1.
Yeah.
Fine. Then, what do we know? If X was the smallest thing that made the statement false, and X minus 1 is smaller than X, X minus 1 makes the statement
True.
Let's say this again. X is the smallest thing that makes the statement false.
Yes.
X minus 1 is even smaller than X.
So it's not A.
So X minus 1 must make the statement
True.
true. X is the smallest thing that makes the statement false.
Yeah. No. Yeah. No.
If 3 is the smallest thing that makes a statement false, then 2 must make it true.
Yes.
Because 3 is the smallest thing that makes it false.
Yes. Mm-hmm.
If Hayden is the shortest person in here not related to me, and Debbie is shorter than Hayden, then Debbie must be related to me. Hayden is the shortest person in here not related to me. You are shorter than Hayden. Therefore, you are related to me. You follow that logic?
Because if you weren't related, you couldn't be shorter than Hayden.
Because if you weren't related, then you'd be the shortest person in the room not related to me. Not Hayden. Did it click? Alright. So let's say this again. X is the smallest number that makes the statement false. Therefore, X minus 1 makes the statement true. You good?
Yeah.
No, make it sing. That is the way math goes 90% of the time. You sit here and you say something and it doesn't make sense, and it doesn't make sense, and it doesn't make sense until it clicks. Then it seems obvious. Alright? So until it feels like I'm just saying something obvious, then you need to keep thinking about it. And we need to keep going over it and coming at it 6 different ways until it feels obvious.
Okay.
Does it feel obvious now? X is the smallest number that makes the statement false. So x minus 1, an even smaller number, must make the statement true. Because if x minus 1 also made the statement false, then it would be the smallest number that made the statement false. So x is our smallest counterexample. So anything smaller than x is not a counterexample. Anything smaller than x makes the statement true. X is the smallest thing that makes the statement false. So x minus 1 makes the statement true. What does it mean for x minus 1 to make this statement true? It means if we add up the first x minus 1 odd integers, then we'll get, if we add the first x minus 1 natural numbers, odd natural numbers, then we'll get x minus 1 squared. Right? That's what it means to make the statement true. It means if I plug in x minus 1 for n, it'd be true. So then, the sum from k equals 1 to x minus 1, the sum of the first x minus 1 odd naturals is equal to, maybe we won't be tricky on this one, is equal to x minus 1 squared. Right? Now I'm going to add to both sides of this expression. Maybe I will write the space here, just so you can see it. So I know that this is equal to x minus 1 squared. I left the space here because I'm going to add something to both sides here in a second. But first, you understand why this is true. Why is this true? Because x minus 1 makes the statement true. So when you plug in x minus 1 for n, the statement must be true. Right? X is the smallest thing that makes the statement false. What does it mean that x makes the statement false? That means if we were to do the sum from k equals 1 to x of 2k minus 1, then we would not get x squared. X is the smallest thing that makes the statement false, so x minus 1 makes the statement true. Good? Alright, so I know that this is equal to this. Now I'm going to add to both sides the xth odd natural number.
The x.
The xth. This is the sum of the first x minus 1 odds. I'm going to add the next odd. This might be 1 plus 3 plus 5 plus 7 plus 9. I'm now going to add 11.
Oh yeah.
I'm going to add the next odd. The next odd would be 2x minus 1. This is the sum of the first x minus 1 odds, and here's the xth odd. If x was equal to 10, then this would be the sum of the first 9 odds plus the 10th odd.
But aren't we stopping at x minus 1? Or are we going higher?
I'm going to add that to both sides.
'Cause if you think
So I knew that this was equal to this, and now I added the same side to both sides, the same thing to both sides, and it should still be equal. You with me? So I knew without that sum, I knew that just because x minus 1 was not an a, and now I'm just adding the same thing to both sides.
Yeah.
So all I've done is add the same thing to both sides. Now, similar to what we had before, if I had the sum from k equals 1 to 4 of 2k minus 1, and then I were to add to that, let's see, what is this? This is 1 plus 3 plus 5 plus 7, right? If I were to add 9 to that, then that would be equal to the sum from k equals 1 to 5 of 2k minus 1. If this is the sum of the first 4 odds, and I add the 5th odd, then it's now equal to the sum of the first 5 odds.
Yeah.
And I could have also written this as, instead of 9, I could have written that as 2 times 5 minus 1. That's still 9, right?
Yeah.
That's just using the same notation we use here. And rather than putting a 4 here, I'm going to put a 5 minus 1 here. Still 4. You with me?
Yeah.
So if I had 5, this is the sum of the first 5 minus 1 odds, plus the 5th odd gives me the sum of the first 5 odds. Similarly, if this is the sum of the first x minus 1 odds, and I add the x odd, I now have on this side, rewriting this side of the expression now, is the sum of the first x odds. This plus this is this. The same way that this plus this is this. Replace my x's with 5, or replace my 5's with x's. If I went through and replace all my 5 with x's, we get the exact same thing up here. The sum of the first 5 minus 1 odds plus the 5th odd is the sum of the first 5 odds. You follow that? So the sum of the first x minus 1 odds plus the x odd is equal to the sum of the first x odds. Which is exactly what I have right here. I'm saying this plus this is that. You follow that algebra? I know algebra with the summation notation to be dense. So this side simplifies to that is equal to, now let's simplify over here. And we're just going to multiply it out. What's x minus 1 squared? Just do the algebra.
X squared.
What is it? X minus 1 times x minus 1? Is that what okay, yeah, but I want you to simplify that. So x minus 1 times x minus 1, what is it? Come on, we've been doing these.
X squared minus x
The
minus
x times the x gives me
X squared.
x squared. The x times the negative 1 gives me
negative x.
minus x. The negative 1 times the x gives me minus x. The negative 1 times the negative 1 gives me plus 1. Or in other words, we get x squared minus 2x plus 1. You guys get to the point where you can just do that in your head.
Yeah.
Right? We did a bunch of these. We did, anytime you have a minus b squared, that's equal to a squared minus 2ab plus b squared. This is just a special case of that where you plug in x and 1.
Mm-hmm.
That's what I'm thinking in my head. Anyways, so when we expand this out, this term out, we get x squared minus 2x plus 1. And then we have plus 2x there. And then we have a minus 1 there. Which is equal to what?
0. X squared.
Right, the negative 2x and the 2x cancel each other out. The positive 1 and the negative 1 cancel each other out. All we're left with is an x squared.
What you wanted.
Which is what we wanted. We just really showed that the sum of the first x odd integers is equal to x squared. Which gives us that what? That x is not in A. Contradiction, because x is the smallest thing in A. Because x makes the statement true.
Mm-hmm.
There's our contradiction. Let's go over big picture what we did one more time. We said let A be the set of all the naturals that make the statement false. Assume by way of contradiction that A is not empty. And let x be the smallest thing in A. So x makes the statement false. But we just really showed x makes the statement true. Contradiction. So x is in A because it makes the statement false, and x is not in A because x makes the statement true. Contradiction. Therefore what?
Therefore, that works with all natural numbers.
Therefore, our assumption is false. Therefore, A is equal to the empty set. Let's not skip steps of logic. When you reach your contradiction, then that means that your beta, we just really showed not beta, we showed alpha and not beta is impossible. And so, we now can conclude that our beta is true. So our not beta was this.
Okay.
So since it can't be not beta, it has to be beta. Therefore, A is equal to the empty set, which gives us that the statement's true. And that being standing for the statement. And we're done. Not going to rewrite that. Make sense? So we just barely showed that the sum of the first n natural numbers is always equal to n squared. Good? Okay. Let's do every other one of these, because I'm not sure how much time we'll have. And we gotta get to the next stuff as well. I don't know, maybe I'll just let you guys pick which ones we do. So, we can prove that the sum from k equals 0 to n, pick any number, like pi, and we're going to prove that pi to the, let's see, we're starting at 0, pi to the 0 plus pi to the 1 plus pi to the 2 plus dot 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 plus pi to the n is equal to pi to the n plus 1 minus 1 over pi minus 1. That's what this statement's proving, where pi is any real number.
Is pi a natural number?
No, I was picking the actual number, 3.14159 dot 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 dot. It's true for pi. I can go through here and replace all my pi's now with some other natural number, or some other real number, I mean, like square root of 2. Square root of 2 to 0 plus square root of 2 to the 1. I can replace it with square roots of 2, and it'd still be true.
But isn't it asking us to prove it with just
No.
naturals?
It's saying for any real number a could be the square root of 2, a could be pi, a could be e, a could be 100, a could be 99.999999999. For any real number a, this is always true, where n is a natural number. As long as a is not 0 and a is not 1. Those are the only two real numbers that make the statement false.
Okay.
But if you were to pick a to be something like 57, perfectly valid. If you were to pick it to be 26 pi, perfectly valid. So that's what this one's saying. This one right here is saying for every natural number greater than or equal to 5, 2 to the n is greater than n squared. And then this one's a proof about Fibonacci numbers. We should probably do that one just to introduce you to Fibonacci numbers. Which of those do you like?
Fibonacci.
Should we skip straight to Fibonacci and we can come back to these two if we want to do them?
Yeah.
Alright, Fibonacci numbers. Let's go over the Fibonacci numbers. Fibonacci numbers are a sequence of numbers. The first two numbers that are in the sequence are 1, 1, 1. And now the next number in the sequence is always determined by adding together the two previous numbers. So what's 1 plus 1?
2.
2. So our next Fibonacci number is 2. Now what's 1 plus 2?
3.
3. So our next Fibonacci number is 3. 2 plus 3? 5.
8.
8. Everyone seeing how this pattern is being generated? 5 and 8 is 13, 21, 34, 55, 89. Right? And we can go on generating forever. It's a very interesting sequence. One that shows up in all sorts of random places. We can't do a deep dive into Fibonacci sequence. Interesting sequence, shows up a lot in mathematics. Okay, here's its actual definition. So Fibonacci numbers are a sequence of numbers f0, f1, f2. Here's f0, f1, f2, f3, f4, f5, f6, da 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 da. So the Fibonacci numbers are some sequence of numbers where the first number, f sub 0, is 1. The second number, which is f sub 1, is also 1. And then from there on out, f sub n is equal to f sub n minus 1 plus f sub n minus 2. The next is equal to the sum of the two previous numbers.
Okay.
So in other words, the 10th Fibonacci number is equal to the 9th Fibonacci number plus the 8th Fibonacci number. That's what this is saying. F sub n is equal to f sub n minus 1 plus f sub n minus 2.
Okay.
You follow that?
Yeah.
Understand the definition? Alright, those are called Fibonacci numbers. Now what are we going to prove? We're going to prove that every Fibonacci number We're going to prove that for all n in n, the nth Fibonacci number is less than or equal to 1.7 to the n. Now that might seem like kind of a stupid, useless thing to prove. Why on earth do I care that the 100th Fibonacci number is less than or equal to 1.7 to the 100? Why would I care about that? Here's why we care about that. 1, 1, 2, 3, 5, 8. How fast is the sequence growing?
Fast.
You have no good intuition in your head for what the 200th Fibonacci number is going to look like. Is that going to be a 5-digit number, a 10-digit number, a 20-digit number? What's it going to look like?
More than one digit.
More than one. You have no good intuition for how fast this thing is growing. And so this gives us an upper bound on it to help us get a quick sense of how it's growing. So when I say, give me a rough idea of what the 200th Fibonacci number is, you have no good intuition from just a sequence, but this right here gives you a quick upper bound on it. And this you can calculate real easily.
Is that saying it's close to 1.7?
No, it's saying it's less than or equal to 1.7 to the n. So we're talking about the 100th Fibonacci number, and I plug that into my calculator, and it comes out with whatever number. Then I know that the 100th Fibonacci number at least can't be ahead of that.
Okay.
So it helps give you a bound on how fast the sequence is growing.
Is that the smallest you could possibly make it? 1.7 to the n?
No, not necessarily,
It's a big.
but it gives you an upper bound. So it's good to know how sequences are bound from above. We have to use this type of thinking all the time. Imagine you have some population growth and you've got to come up with some fencing for how much cattle you have there, and you want that fencing to last you for the next 10 years. You're going to need to know what the population growth of that cattle is going to be and how much they're going to need to consume over the next 10 years. Fibonacci numbers happen to be related to rabbit repopulation. It's not intuitive how, but yes. So Fibonacci numbers come up a lot naturally in mathematics. It's very useful to know at least how they're bounded from above, because it's very hard for us to get any intuition for how the sequence grows. Right? So let's jump into this proof. 1. What's our first line?
Let A equal.
Let A be the set of all the natural numbers that make the statement false. So let A be the set of all natural numbers such that that Fibonacci number is greater than 1.7 to the n. It's not less than or equal to it. It's greater than it.
Okay.
Obviously we know A is false. If we prove, obviously we know A is empty, so assume by way of contradiction that A is not empty. Assume by way of contradiction that A is not equal to the empty set. Okay, well then what does that give us? If A is not empty, it has a least element. That implies A has a least element. Call it X. Okay? Observe that. What's the first Fibonacci number?
1.
F sub 0, which is equal to 1, is less than or equal to 1.7 to the 0. And F sub 1 is equal to 1 is less than or equal to 1.7 to the 1. F sub 0 is 1. The first Fibonacci number is 1, right?
Yeah.
What's 1.7 to the 0?
1.
1. Is 1 less than or equal to 1?
Yes.
Yes. Let's look at the next one. What's F sub 1? What's the second Fibonacci number?
1.
1. Is that less than or equal to 1.7 to the 1?
Yes.
Okay. So I know that X, whatever X is, has to be greater than or equal to 2. It has to be at least the second Fibonacci number. Because the first two Fibonacci or it has to be at least the third Fibonacci number.
Yeah. Yeah.
Because the first two Fibonacci numbers
Or 0.
make the statement true.
Oh.
X is the smallest thing that makes a statement false. So the smallest thing that makes a statement false has to at least be when n's 2. Can't be when n's 0, can't be when n's 1. Maybe when n's 2 the statement's false, but for sure, not at 0, not at 1. Right?
Okay.
So X has to be greater than or equal to 2. Do we need to do one more? I'm not sure if we need to do one more. Let's just write it out, just because it's easy to check. And what's f sub 2 equal to?
Minus 1.
It's equal to 2, which is less than or equal to 2.89, which is equal to 1.7 squared. So the second Fibonacci is less than or equal to 1.7 squared. 1.7 squared is 2.89.
2 point. Okay.
What's 17 squared? 209.
Oh yeah.
Shift the decimal place twice.
You know that, okay.
17 squared.
Yeah, we're not just.
You don't have a bunch of your squares memorized?
I guess I went 7 squared to 49.
Okay. So whatever that gives us that x has to be greater than or equal to 3, which gives me x minus 1 has to be greater than or equal to 2. We don't even need that. Sorry. 4. Then f sub x. So I just needed that. I just need that x is greater than or equal to 2. That is all I needed. Because I need us to be using this definition for x, not this definition. So how do we calculate f sub x? We use this definition over here. It's not one of the ones. So every Fibonacci term is calculated by the first two terms, f sub 0 is just 1, and f sub 1 is just 1. But now f sub 2 is defined to be f of 1 plus f of 0, right? And f of 3 is defined to be f of 2 plus f of 1. Okay, so we need to make sure x isn't one of those two cases. It's down here. So the definition of x, since x is greater than or equal to 2, then that means 4, then by definition, f sub x is equal to f sub x minus 1 plus f sub x minus 2.
Okay.
You with me?
Yeah.
Now, x is the smallest Fibonacci number that makes this inequality false. Which means this Fibonacci number and this Fibonacci number make the inequality true. So then I know f of x is equal to that, but I also know that f sub x minus 1, I know that is less than or equal to 1.7 to the x minus 1. I know that for x minus 1, this inequality is true. And I also know it's true for x minus 2. Everyone understand that? F sub x is equal to some of these two things. I know the statement is true for the x minus 1 Fibonacci number, and I know the statement is true for the x minus 2 Fibonacci number.
Yeah.
Because the smallest Fibonacci number that it wasn't true for was f sub x. So it's true for f sub x minus 1, and it's true for f sub x minus 2. You with me?
Yeah.
Okay, 5. Then f sub x, which is equal to f sub x minus 1 plus f sub x minus 2, must be less than or equal to 1.7 to the x minus 1 plus 1.7 to the x minus 2. If this is less than or equal to that, and this is less than or equal to that, then the sum of this is less than or equal to the sum of this.
And fx equals that.
So f sub x is less than or equal to this thing. Now, we're not done. What are we trying to show? Right up here. We're trying to show that f sub x is less than or equal to 1.7 to the x. That's what we're trying to show. So far I have it's less than or equal to this thing. Now, I'm going to do some algebra. I'm a little worried you might not follow. Let's write a concrete example of it really quick. if I have a to the 5 minus 1, well, let's just write it as 5 for a second, plus a to the 4, I can rewrite this as, I can factor out of these two terms as a to the 4. And if I take 4 a's away from this a, how many am I left with?
Just one.
1, just a. And if I take 4 a's away from this, what am I left with?
The number 1.
Just 1. You see that? If I redistribute it, a to the 4 times a gives me a to the 5, plus a to the 4 times 1 gives me a to the 4.
Okay.
Now I'm going to replace that 5 with a 5 minus 1, and that 4 with a 4 minus 1.
Okay.
Maybe I'll say it this way so we say the same numbers. I'm going to rewrite that as a 6 minus 1 and a 6 minus 2. And it's still true, right? That's still 5 and 4.
Yeah.
I'm going to rewrite this 4 as a 6 minus 2. Still true, right?
Yeah.
Everyone with me?
Okay.
Now, I can replace 6 with any number and it will be true. I can replace it now with a 10. A to the 10 minus 1 plus a to the 10 minus 2 is equal to a to the 10 minus 2 times a plus 1. So I'm going to replace that with an x, that with an x, leaves an x here. Follow that?
Yeah.
That's what I'm going to do here. I'm going to factor out of these two terms a 1.7 to the x minus 2. So that is equal to a 1.7 to the x minus 2 times, from this one we still have a 1.7, plus, and from this we just have a 1. There's a decimal there. That's just using this exact same algebra.
Okay.
A to the x minus 1 plus a to the x minus 2 is equal to a to the x minus 2 times a plus 1. Follow that? What's 1.7 plus 1?
2.7.
2.7. So this is equal to, I'm just going to write the 2.7 first. 2.7 times 1.7 to the x minus 2. You go with that?
Yep.
Which is less than or equal to 2.89 times 1.7 to the x minus 2. If I make that number bigger, then we obviously made it bigger. Which is equal to 2.89 is the same thing as 1.7 squared times 1.7 to the x minus 2. Now, when you multiply terms together, you add the exponents. What's 2 plus x minus 2?
X.
1.7 to the x. There we go. So, what did I just really show? I showed f of x is equal to this, is less than or equal to that, is equal to that, is equal to that, is less than or equal to that, is equal to that, is equal to that. Or in other words, I showed f of x is less than or equal to 1.7 to the x. So x makes the statement true. You with me? X was the smallest thing that made the statement false. So it has to look like this when I plug in an x. We should have f of x is greater than 1.7 to the x. I just showed that f of x is less than or equal to 1.7 to the x.
Yeah.
Contradiction. Therefore, a is empty. Therefore, this is true for all the Fibonacci numbers.
Okay.
Follow it?
Yep.
All right, let's move on to induction. And we can come back and do more of these problems if we have time. But we've got to cover induction because you guys have a test next week. And induction will be on the test.
Isn't there text today too?
Yeah, but that's just a retake. That's not a... It's not a scheduled test. I cannot see on my camera. Hopefully we got it all. Okay. Principle of induction now. Next section, principle of induction. Here's how the principle of induction works. Confuses students, but it's such a simple concept. Imagine I have some secret set, I call it A. So A is some secret set, I'm not going to tell you what's in there. You have to figure out what's in there. But I'm going to give you 2 hints about what's in there. I'm going to tell you that 0 is in there. And I'm going to tell you that anytime some number k is in there, the number k plus 1 is also in there.
Okay.
So if you can ever find some number in there, that same number plus 1 is also in there.
So 0 plus 1 plus 2.
So you know that 0's in there, so you know that 0 plus 1's in there, so you know what else is in here.
All the natural numbers.
Well, let's not jump ahead. But yes, that's the point. So I know 0's in there. And I know that anytime I can find some number k in there, that same number plus 1 must also be in there. So 0's in here, so what else is in here? 1 is in there. What else is in there? 2. How do you know 2's in there?
Because 1 plus 1 is 2.
Oh, that works. Okay, so 2's in there. What else?
3.
3? How do you know?
2 plus 1.
So 3's in there. And 4. And dot, dot, dot. And you see what Jeremy was saying. It's the natural numbers. Right?
Yeah.
So if you can find a set that has this property, it has 0 in it, and every time k is in it, k plus 1 is also in it, then what you have is the natural numbers. Feels to your intuition? Feels almost obvious?
Yeah.
Good. Feels almost obvious. Now let's prove it. Never prove something unless it feels almost obvious. As I'm proving, make sure you understand exactly what we're saying. So, let A be a subset of natural numbers, such that 0 is in A, and every time k is in A, k plus 1 is also in A. With me? Obviously, we're talking about this set right here. Now, let B be the set of all the natural numbers that aren't in A. So B is, take all natural numbers, now get rid of everything in A.
But that's all the natural numbers.
Exactly, B is an empty set. We're going to be doing smallest counterexample proof. B is going to be operating the way that A operated in all the proofs over here. Okay, so yes, B is empty. There's nothing in there. Let B be all the natural numbers that aren't in A. And assume by way of contradiction that B is not empty. We know B is empty. Assume by way of contradiction that B is not empty. If B is not empty, what does that mean? It has the least element, call it X. Right? Since 0 is in A, how do I know 0 is in A?
Because it said so.
Because we said so right there. That's a great reason. So since 0 is in A, then whatever X is, it has to be greater than 0. Right?
Yeah.
Which means X minus 1 is the natural number. Okay, so I know X minus 1 is a natural number. And so X minus 1 is in A. X minus 1 is a natural number.
Why do you know that if X could be 0? Oh, never mind. Okay.
X minus 1 is a natural number. It's not in B, because X is the smallest thing in B, and so it has to be in A. Look, we basically divided all our natural numbers up into sets A and B. B is a set of all the natural numbers not in A.
Yeah.
Right? So every natural number is either in A or B.
Yep.
X is the smallest thing in A, so X minus 1 must be in
B.
Oh, you're right.
B. Yes, B. So, oh, I said that backwards. No wonder you're confused, because we're switching our sets. X is the smallest thing in B. Right?
Yeah.
Assume by way of contradiction that B is not empty and B has the least element, call it X.
Oh.
Sorry, that's my bad. So if X is the smallest thing in B, then X minus 1 must be in
A.
A.
And that means A is not empty.
So that gives us that X minus 1 is in A. Now A has a special property that if I can find any number in A, that number plus 1 is also in A. Right?
Yeah.
So if I know that X minus 1 is in A, what else do I know is in A?
X.
X minus 1 plus 1.
X minus 1 plus 1, which is just
X.
X. So I have X is not in A and X is in A. Contradiction. Therefore our assumption that B is empty is false.
Where was it said that?
Or that b is not empty is false. Sorry, what?
Where was it said that x is not an
We said that b has the least element x. X is in b,
It's in B, so
and b is everything not in a.
Yeah.
I see that.
Okay, so we have x is not in a, but down over here, since x minus 1 is in a, then x minus 1 plus 1 is in a, or in other words, x is in a. So we have then x is not in a, and x is in a. Contradictions. Therefore, our contradiction, or therefore b must be empty. We assumed b wasn't empty, that led to an impossible worldview. Therefore, b must be empty. Remember how proof by contradiction works. We show alpha and not beta, and not beta leads to an impossible worldview. Therefore, if you have alpha, you must have beta. What was our beta statement? B equals the empty set. So we assumed not beta, B is not the empty set. Showed that was impossible, therefore B is the empty set. And therefore, if B is an empty set, that means A and the natural numbers are the same set. If I take all the natural numbers and I minus A and I'm left with nothing, then A must have been all the natural numbers. Good? Alright, so we just already proved it. We just already proved that if a set A has these two properties, then that set A is equal to all the natural numbers. Any questions on that?
Is that just proving it's part of the natural numbers? Is that proof by induction? Or what was the actual proof of induction?
We just barely proved this principle right here. Now we're going to use that principle to prove other things, and we call that a proof by induction. So now I can show that if some set, so I take some set of numbers that has a property. If I can show that that set of numbers satisfies this rule and satisfies this rule, then that set of numbers is the natural numbers. So I say, let A be the set of all the natural numbers where this is true. If I can show that 0 is in A, and I can show that if k is in A, k plus 1 is in A, then A is all natural numbers, and so the statement is true for all natural numbers. That's how we're going to be doing it. So let's walk you through a proof by induction example. Here's the typical one that you do first for every proof by induction, so we'll do this one first. So we're going to do the proof now that for all natural numbers, for all n and n, the sum from k equals 1 to n of k is equal to n times n plus 1 over 2. In other words, what are we saying? I say, Jeremy, I want you to add up all the numbers between 1 and 100.
Okay.
How would you do that?
Calculator. A lot of time.
With a calculator, a lot of time. That would be a very, very stupid way to do it.
Probably.
Instead, we can use this formula. Give me an intuition for this formula. If I'm going to add up all the numbers between 1 and 100, how would I do that? I could do 0 plus 1 plus 2 plus 3 plus 4. Show you why I started with 0 in a second here. Plus dot 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 plus 96 plus 97 plus 98 plus 99 plus 100. Right? Now I just pair them off. What's 0 plus 100?
100.
What's 1 plus 99?
100.
What's 2 plus 98?
100.
What's 3 plus 97?
100.
What's 4 plus 96?
100.
All the way down to, eventually in the middle, we have 49.
49.
No, you don't get 50-50. 50 only shows up once.
Okay.
49 plus 50 plus 51. And I would be saying, what's 49 plus 51?
100.
And you're left with the 50 in the middle. So how many pairings of 100 did I make?
490.
50. I paired 0 with the 100. 1 pairing. 2 pairings. 3 pairings. 4 pairings. 4 pairings. 5 pairings. Dot, 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 dot. 50 pairings. Why 50? Because I did all the numbers from 0 to 49.
So it's 5,000.
So that's 50 numbers.
Yeah.
5,050.
So we did 50 100s plus a remaining 50. Right?
Yeah.
Another way that we could have written that was for we could use this trick for any n. In our case, n was 100. So that's n over 2 times n plus n over 2. Factor out the n over 2 from both of those. and you get n over 2 times n plus 1, which is exactly what we have over here.
Nothing.
Right? Just write the n over 2 by itself, pull the n up plus 1 over by itself, same thing.
So that's the proof.
No, I just give you good intuition for it. This is, the discovery of this formula is credited to Gauss. And the story goes that back when he was in basic arithmetic, so just a little kid, his teacher was just trying to give a bunch of students a bunch of busy work. So he told them to add up all the numbers between 1 and 1,000.
Oh, land.
And so, yeah, Gauss thought about it for a minute. And he wrote on his blackboard just one number.
Smart guy.
And gave it to the teacher, and then I guess was accused of cheating. Don't remember how the story goes.
How old was this? How long ago?
Gauss?
Yeah.
Gauss is 18th century.
Yeah, he probably just pulled it up on his phone or something.
Ah yeah, he Googled it real quick.
Yeah, that's how.
You cheat.
Anyways, so let's do the proof of this. So how to do this? 1. This time once again, we're going to let A now be the set of all the natural numbers that make the statement true this time. A is going to be a set of all the natural numbers that make the statement true. And then I'm going to prove that A contains 0. And I'm going to prove that anytime A contains K plus 1. Therefore, we know that A is equal to all natural numbers. Therefore, all natural numbers make the statement true. That's our logic. So let A be a set of all natural numbers such that this is true. Set of all natural numbers that make that statement true. I'm going to prove that A is all natural numbers. Therefore, the statement is true for all natural numbers. Make sense?
Yeah.
So I need to prove that A has these two properties. I need to prove that 0 is an A, and then I need to prove that if K is an A, K plus 1 is an A. And we're done. That's why proof by induction is so nice. So 2, observe that what note I should have made here. What if instead of starting at 0, I told you 1 here? So I told you A is a secret set, and A starts with 1, and now every time it has K, it also has K plus 1.
That's not all the natural.
Then it's 1, 2, 3, ... and instead it's all the positive integers rather than all the natural numbers, right?
Yeah.
So this one, I think we're actually proving about all the positive integers, because I think we're starting at 1. That's how I have it written there. Although we could start at 0. Sorry. I can do K equals 0 here. We can start at 0. Nothing wrong with starting at 0. Sorry. Don't want confusion. Shouldn't have done that. Go with action, start at 0. Let's do this. Okay, so now observe that the sum from K equals 0 to 0 of K is equal to what?
0.
Plug in 0 for K. What do we get?
0.
0, and stop when K reaches 0. So it's just 0.
Yeah.
Is equal to 0 times 0 plus 1 divided by 2,
Which is 0 over 2. 0.
which is equal to 0. So this is equal to 0, this is equal to 0, therefore this is equal to this. Therefore 0 makes a statement true.
Yeah.
So I just barely showed that 0 makes a statement true. In other words, 0 is in A. Since A is the set of all the naturals that make the statement true. So I showed my first property. I showed that 0 is in A. Now I need to show that if K is in A, K plus 1 is in A. And then we're done.
So 0 is an 8. We need to show 1 is an 2.
No. We need to do it in general.
Why? Oh, never mind.
I can't do infinitely many proofs.
Yeah.
I need to do just one proof. So I need to show that if K is an A, then K plus 1 is an A. This is an if-then statement. How do we prove an if-then statement?
Implication.
How do we prove an implication?
By
Probably said this 100 times in this class.
assuming the antecedent.
Assume the antecedent and show that implies a conclusion.
Yeah.
That's how you prove an if-then statement. So now we assume the antecedent, assume K is some number in A. If K is in A, what do we know?
That K
K plus 1 is
plus
an
one is
A.
an A.
No, we need to prove that.
Then it follows that formula.
Yeah, but it's the principle of induction.
We are proving that this set
Oh, you're right, you're right, you're right.
has these properties. That's what we're trying to prove. So I didn't magically know 0 was an A. I showed 0 was an A. Now I'm going to show that this principle holds for this set A. And therefore this set A is all the natural numbers. So assume K is an A. What is A? Over here, what is A?
A set.
So
It's a
It's
s-
set of all natural numbers.
That what?
That satisfy that.
That satisfies the statement. So K satisfies the statement. Ooh, let's not use K since we use K in our formula there. We'll use X. So I'm going to show X in A implies X plus 1's in A. So since X is in A, X makes the statement true. Or in other words, if I were to do the sum from K equals 1 to X of K, it would be equal to X times X plus 1 over 2. Right?
Yeah.
All right. Well, what does that give me? I'm going to add K plus 1 to both sides of this expression. Or X plus 1 to both sides of this expression. So here we have the sum from K equals 1 to X of K. And I'm going to add to that X plus 1. And that is going to be equal to this thing plus X plus 1. Everyone see what I did? I took this, and I just added X plus 1 to both sides. Right? Now, what is this right here? This is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 all the way up to
X.
X. Right? And now I just added X plus 1. So now, this left-hand side is the sum from K equals 1 to X plus 1 of K. It's now 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way up to X plus 1. This and this are the same thing.
Yep.
You see that? I just added the next term. So that is now equal to, so this side simplifies to that. What does this side simplify to? Well, first let's get a common denominator. So this is going to be X times X plus 1 over 2. I'm going to multiply this top and bottom by 2. So plus 2 times X plus 1 over 2. So I just multiplied this top and bottom by 2. Right? Now they have a common denominator. So I can write them all over 2. Let's distribute. X times X is X squared. X times 1 is plus X. 2 times X is plus 2X.
It's
2 is 2, and it's all over 2, right?
Yep.
Which is equal to X squared plus 3X plus 2 over 2, right?
Yeah.
Which is equal to, now we factor this. We're going to factor this, so we're going to have X over 2. These two numbers multiplied together have to give me that, and these two numbers added together have to give me 3.
It's 2 and 1.
So 2 and 1. 2 and 1. 1 times 2 is 2. 1 plus 2 is 3. Okay. But what does that tell me? That tells me that X plus 1 is an A. X plus 1 makes the statement true. The sum from K equals 1 to X plus 1 of K is equal to X plus 1 times X plus 1 over 2. Oh, sorry, I wrote it backwards.
Yeah.
But we get one.
Put the 1 here and the 2 here, and now it follows this formula.
Well, now it works.
X plus 1 times X plus 1 over 2. The sum from, sorry, K equals 0. Why do I keep doing 1? We start at 0. The sum from K equals 0 to X plus 1 of K is equal to X plus 1 times X plus 1 all over 2. Right? Which finally gives me, therefore X plus 1 is an A. Therefore, using the principle of induction, A is equal to the set of all natural numbers. So the statement is true for all natural numbers. And that's how proof by induction works.
Cool.
Cool? Let's do one more, and then we'll call it. One of those you like?
Factorial.
This was one, yeah, the factorial one. This was one that you guys, in your homework, you were supposed to make the conjecture that this was true, but not prove it.
Right. That's
So let's actually prove it now. You guys remember that problem?
I think so.
You think so?
no.
Those of you who actually did your homework, you remember that problem?
Wasn't it an extra credit?
No. You were just making a conjecture. They had you calculate 1 times 1 factorial, 2 times 2 factorial, or 1 times 1 factorial, 1 times 1 factorial, plus 2 times 2 factorial, 1 plus 1 factorial, plus 2 times 2 factorial, plus 3 times 3 factorial. And they had you manually do those calculations. And they said, make a conjecture. Here was your conjecture.
Of what?
And so now we're going to prove the conjecture. So we're going to prove that for all natural numbers greater than or equal to 1, this one we're going to start at 1. And you'll notice they did as well if you go back and look at the problem. They didn't start at 0. For all natural numbers greater than 1, comma, the sum from k equals 1 to n of k times k factorial is equal to n plus 1 factorial minus 1. Let me write a concrete example of what we're saying here. We're saying that 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial would be equal to 4 factorial minus 1. There's a concrete example if we plug in 4 for n. Make sense what we're proving?
No. I had to stop at 3 factorial on the left side. Now you go to 4 factorial. Your n is 4.
Oh, sorry. My n was 3. Plugging in 3 for n.
And yeah, makes sense.
Okay, good catch. So plugging in 3 for n, there's our concrete example. We're going to prove that this is true no matter what. We're going to use proof by induction. So 1. Let A be the set of all the natural numbers, all the n's greater than or equal to 1. We're going to start this one at 1, such that this is true. 2. What are we trying to show about A? I'm trying to show now that 1 is in A, and if k is in A, k plus 1 is in A. Therefore, every natural number greater than or equal to 1 is in A.
1 or 0?
This time we're going to start 1.
But you can still use the principle.
We can still use 0, because 0 times 0 factorial would just be 0. So, this one actually is true for all natural numbers. Oh wait, we get 0 over here. 0 plus 1? Yeah, we get 0. So it's true for all natural numbers. We don't need to say all natural numbers greater than or equal to 1. Okay. So let A be a set of all natural numbers. That makes the statement true. 2. Observe that the sum from k equals, this time we'll say 0, from k equals 0 to 0 of k times k factorial is equal to 0 is equal to 0 plus 1 factorial minus 1. This is equal to 0. This is 1 minus 1 is 0.
Okay.
So that gives me that I now know 0 is in A. So we showed the first step. We showed 0 is in A. Next thing we need to show is that if k is in A, k plus 1 is in A. How do we show that?
By showing like k,
Assume
assuming k is in
Assume, perfect. But yeah, we're going to use x instead of k since we've already used k. Assume x is in A. If x is in A, what does that mean? That means the sum from k equals 0 to x of k times k factorial is equal to x plus 1 factorial minus 1. Right?
Yes.
If x is in A, x makes the statement true.
Yes.
Okay, now what am I going to add to both sides of this expression? X plus 1 times x plus 1 factorial. So then that gives me, we have the sum from k equals 0 to x of k times k factorial. I'm going to add to this side x plus 1 times x plus 1 factorial. And that has to be equal to this side when I add the same thing. X plus 1 factorial minus 1 plus x plus 1 times x plus 1 factorial. So I added x plus 1 times x plus 1 factorial to both sides of this equation. That's all I've done so far, right?
You're also adding x plus 1.
I added this to both sides.
Yeah.
X plus 1 times x plus 1 factorial to both sides.
Why aren't you just doing x times x factorial?
Because now this simplifies to what we want. So over here now we have the sum from k equals 0 to x plus 1 of k times k factorial.
Okay.
This is equal to this and this. This is writing out the first x terms plus the x plus 1 term. Do you see that? Am I losing you guys on this notation again?
No, I can't.
Oh, you're good? Okay. And that is equal to, over here, let's simplify. We have an x plus 1 factorial. I want you to think about that x plus 1 factorial as a SpongeBob for a second.
Okay.
Alright? So I have SpongeBob minus 1 plus this many SpongeBobs. If I have x plus 1 SpongeBobs and another SpongeBob, how many SpongeBobs do I have?
X plus 2 SpongeBobs?
Yes. So I have SpongeBob and I have x plus 1 SpongeBobs, add them all up, and I have x plus 2 SpongeBobs.
Oh yeah, easy.
And then we still have our minus 1 there.
Okay.
So I had 1 x plus 1 factorial, and I had x plus 1 factorials for a total of x plus 2 x plus 1 factorials.
Wouldn't the x plus 2 be on the factorial one, because they're both factorials?
X plus 2 is a factorial.
You have x plus 1 factorial.
Yes, I have x plus 2 times x plus 1 factorial.
Why does the one that does not have factorial attached to it get the bonus 1?
Look, pretend that x plus 1 factorial, we just replace that with some variable y.
Okay.
So I have y plus x plus 1 y's. How many y's do I have?
2.
X plus 2 y's.
Yes.
X plus 2 y's.
Oh,
Okay, I see that.
Good?
yeah.
Okay. Now, what is it? What is x plus 1 factorial? That is x plus 1 times x minus 1 times x minus 2 times x minus 3 all the way down to 1. So if I multiply it by an x plus 2, what is that?
X plus 2 factorial.
It's just x plus 2 factorial. This is multiplying all the numbers starting at x plus 1 going down. Right? Now if we add at the top x plus 2, now we're multiplying all the numbers starting at x plus 2 going down. So this is just x plus 2 factorial minus 1. Follow that?
Yes, sir.
Yes.
And that gives us what we want. That gives us that x plus 1 is an a, which gives us that a is equal to all natural numbers.
Screwbox.
Good? Alright, these proofs are tough, they're a pain. These are some of the false proofs you're going to have to do in the class. Everyone hates proof by induction the first time they come across it, but when you get to higher math classes, believe it or not, it's one of the first ways you check to see if you can prove something because you learn to love it and it's your favorite way to prove it because it's so straightforward. As unintuitive as that seems.
What are the higher classes?
Higher classes, like real analysis, for example, if you could do this, topology, computation theory,
Calculus.
proofs in calculus, which we call real analysis. Real analysis is proving calculus. You don't have to do so much in typical calc course. Remember that this class is considered higher than a calc course.
It is?
Yes, at university you would be required to take Calc 2 before they let you take discrete math.
Calculus 2.
Yes, Calculus 2. Because Calculus 2 is where you get really comfortable with sequences and series. So the summation notation doesn't throw you for a loop at all. For you guys, that summation notation is going to kick your butt,
Yeah.
which is understandable. It's not because it's hard, it's just it's dense. There's a lot of notation going on, and so you every time you see it, you got to stop and think, wait, what exactly is that saying?
Yeah.
Which is understandable. It's pain for everyone the first time they come across it. Well, almost everyone. There's your Einsteins, who never had problems with it, in spite of what people say.
Right.
Right. So, that's it. We won't spend any more time on this. Any questions? All these are proved in the book. So you can find proofs of all of them. No questions? All right.